Hello people, continuing with integration. So here, now we're actually going to be using trig identities. So we're going to integrate here tan squared x but with respect to x. Now sometimes, as we mentioned earlier in the last video, that you have to manipulate some equations in order to rewrite them in the form of factors which you can integrate. So here we've got tan squared x. We can't integrate tan squared x directly, but what we can do is we can rewrite it as sec squared x minus 1, because we know that 1 plus tan squared x is sec squared x. So tan x, obviously, then we just integrate that by just separate parts, so we get tan x minus x plus c. And in the next example, we have integral of sine squared x with respect to x. So here we can't really integrate sine squared x, and we have to use the identity of cos 2x is 1 minus 2 sine squared x. And when we rearrange that, we get 1 over 2 minus a half cos 2x, and then we integrate that, so we get a half x minus a quarter sine 2x. Now what we also need to know is using partial fractions, which is earlier on in C4. So here in the example we have x minus 5 over x plus 1 over x minus 2. You can watch this video because I'll go over partial fractions anyway. It will be a good recap. So we essentially rewrite x minus 5, x plus 1, x minus 2 in terms of one term over x plus 1 and one term over x minus 2. The reason why we do that is because when we add fractions together, we actually times the denominators if we can't find any common factors. So here we can rewrite this as a into x minus 2 plus b into x plus 1 all over x plus 1 x minus 2. So that must mean that a into x minus 2 plus b into x plus 1 must equal x minus 5, right? So here we're going to let x equal 2 so we can eliminate the a. So then we just get minus 3 is 3, b is 1, minus 1. Now also we're going to have to now eliminate the b in order to work out a. So if we let x equal minus 1, minus 6 is minus 3a plus 0, a is 2. So now you can rewrite this as 2 over x plus 1 minus 1 over x minus 2. And then we can integrate that. Now the reason why we've done this whole process is because you can't really integrate. You couldn't have integrated the fraction as it was before, because it was two terms timesing together. What we've done is we've separated the fraction, hence why we have partial fractions, so that we can easily integrate it. So here we've got the integral of 2 over x plus 1 minus 1 over x minus 2, so that gives us 2 ln x plus 1 minus ln of x minus 2. So here, the whole point of substitution is basically to simplify a really messy expression that we need to integrate. So we essentially let u or something equal something else, and then we integrate that, and right at the end we just put it all back in and we've integrated that function. So here we've got the integral of 2x over x squared plus 1 with respect to x. So here what we do is we let u equal ln x squared plus 1. The reason why I say that is because normally when you actually have a fraction, you always think about ln. The whole point of substitution is identifying trends, and the more you practice that, the better you'll become. So here we're gonna, first step is differentiate that, so we get du by dx is 2x over x squared plus 1. Now what we've actually found out, we've actually matched the original equation. So essentially we can just let I, which is what we've let it originally, equal ln x squared plus 1, because when we differentiate that we will get 2x x squared plus 1. Substitution is sort of and trial and error. Sometimes you get it, sometimes you don't. So anyway, next we're going to be doing letting I equal the integral of x into x squared plus 5 all cubed. Now here we're going to let u equal x squared plus 5 to the power of 4. And then what we're going to do is redifferentiate that. So we get 4 into 2x into x squared plus 5 all squared. And then what we do is we can say I must be equal to an eighth of x squared plus 5 to the power of 4. The reason why we say that is because we've just found out that du dx is 8x x squared plus 5 all cubed. And if we look at the original equation, that is x into x squared plus 5 all cubed. So they're pretty much the same, except we've just got an 8. So all we need to do is cancel out that 8, so we just do 1 over 8. Hence we just have I is equal to 1 over 8 x squared plus 5 to the power of 4. All we're doing here is we're seeing, using trial and error, seeing if something differentiates us to get our function, which is x squared plus 5 to the power of 4. Power of 3, sorry. Now in the next example we've got a slightly more complicated one, so we got u equals 2x plus 5. When we differentiate that, which is our first step, du dx is 2, so dx is a half du. Now this is slightly different because we can't go directly back to the answer, it's slightly more complicated. So here we're gonna rewrite x in terms of u, and then sub that back into the equation. So we got integral of u minus 5 over 2 times by root u times by half du. The reason why we have to do the du by dx is so that we can say it's with respect to x, because whenever you're integrating, you should know that every term that you're integrating, it should be with respect to that same term. That's what du or dx means. So now we pull out the quarter. That's what you should always do, pull out your constants so you're less likely to make a mistake. And then we have u to the 3 over 2 minus 5 u to the half, and then we integrate that, we get 2 over 5 u to the power of 5 over 2 minus 5 over 6 u to the power of 3 over 2 plus c. So I is equal to a tenth of 2x plus 5 2.5 minus 5 over x 2x plus 5 plus c. Hope you enjoyed that video. Please do ask me for any more questions that you have, and soon I will be uploading integration by parts.